Good morning, everyone. Welcome to the Naperville Astronomical Association's Sunday session on the sun. We're going to look at a different star than what we've been doing lately and look at the daytime star. I have, let me see if I can get you a picture of, I have a comrade in all this. Our Vice President, Jim Erwin, is out in his backyard with his solar imaging setup, and he's going to be providing us some live views of the sun while I sit in the control room here and share some other images and information about our nearest star, the sun. So, without further ado, we've got a lot of stars that we look at in the nighttime sky, and they're all very far away. And they all look like pinpoints. And it'd be really neat if we could get close to them and see more details of what they look like. And fortunately, we have a star that's really close to us. Instead of being light years away or thousands of light years away, the sun is only 8 light minutes away. So we can see it quite close up in quite good detail. This is a really quick overview of what we know about the sun and what we see on it. So this diagram from NASA here is a cutaway view of the sun. This section up in the upper right-hand quadrant here is showing the surface of the sun that we see if we look at the sun with a close-up telescope from the Earth. Let me see if I can get this all straightened here. So we have the surface that's a yellow star. It's actually technically a green star, but the yellowish looking of the surface of the sun with some sunspots on it. And that's pretty much the detail we see there, but there's a lot more going on in the sun than that. And we're going to take a look at it in a different light today. The furnace of the sun is down in the core. The energy from that nuclear furnace going down there takes a long time. It takes tens of thousands of years to make its way out to the surface and shine just from its heat. The sunspots are slightly cooler areas. This bright photosphere of the sun we see is about 10,000 degrees Fahrenheit in temperature. The sunspots are a little dimmer just because they're a little cooler, so they don't shine as brightly. They might run from around 7,300 degrees to around 8,000 degrees. They're still really hot. You wouldn't want to go there and stand there, but they're not quite as hot, so they don't shine quite as brightly. What causes sunspots? I'll get into that a little bit more later, but basically those cooler areas are where the magnetic lines of the sun are knotted together and they slow down that flow of heat from the inside out to the surface. So not as much heat radiates there, so it's a little bit cooler. We're also going to look at this atmosphere of the sun, which is shown as this next layer here. It's called the chromosphere, and it's much fainter, the light from it, than the bright photosphere surface that we see of the sun. But we're going to look at it in a special color of white and called hydrogen alpha light. And that enables us to see the boiling hydrogen gas that is seething off of this hot surface, and some of it ends up streaming out into space. So those are going to be our targets today. And we'll look at the surface that we normally see, and then the atmosphere right above it, the chromosphere. How we look at this fainter, hotter, actually it's not hotter gas, the chromosphere is about 7,800 degrees Fahrenheit or so. But how we see that is that this gas is almost all hydrogen, and hydrogen glows when it's very hot in very specific wavelengths. This is the spectrum of what sunlight would be like if you break it up in a rainbow or with a prism. It's just continuous because it's a hot body. It glows like a hot piece of metal or anything would when you heat it up to that 10,000 degrees that surface is at. But the hydrogen itself interacts with light by glowing when it's that hot at very specific wavelengths. These lines that are into the ultraviolet here, this line in the blue here, and this line in the red here. This is what we're going to be looking at today. So the hydrogen is glowing in that color instead of in this whole broad spectrum. Also, when this light shines through that hydrogen gas, the hydrogen absorbs the light in those colors. So there ends up being a band in the sun spectrum that looks like a dark band because the hydrogen is absorbing that light. So what we do is we build a telescope that only looks at that color light. So basically it dims out all of this other bright light of the surface of the sun and only shows us that glowing hydrogen. So we call that a hydrogen alpha observation, or with a hydrogen alpha telescope. That's one of the scopes that Jim's got set up in his yard today. And it allows us again to see that atmosphere, which otherwise this bright light of the whole surface of the sun would be hiding from us. And so we're going to take a look into that atmosphere streaming off the sun. If we look at the sun in other wavelengths, we can see all sorts of other layers of the atmosphere and other details. These are images, these are the most current images taken by a orbiting solar observatory satellite, which is always watching the sun and can view at a number of different wavelengths, which basically show different temperatures and different elements in the solar atmosphere. This is a view basically in what would be like white light of the sun pretty much right now. The face of the sun has very little going on it now. The sun goes through a cycle of the sunspot activity and the other surface activity from those magnetic effects on the surface of the sun. The cycle takes 11 years to go from peak to peak. We are right now in the basement, in the trough, at the minimum of that cycle. We're waiting for the next upswing to happen and more sunspots to come back. But there's one little sunspot group down here in the corner on the face of the sun today. Not a whole lot else going on. I'm going to go ahead and let Jim switch over to his camera setup. I guess I need to spotlight him. I'm going to stop sharing this screen. I'm going to go to Jim's There we go. So we're looking at the edge of the sun in live view through Jim's hydrogen alpha telescope. And so the white disk is a portion of the sun. The edge shows there, and there are things hanging off the edge of the sun. What are the things hanging off this edge? Well, they are prominences. They are gas jets blowing up off the sun from active areas. He's got what's basically the top limb of the sun showing here, right towards the top pole of the sun. There are some nice prominences going on right at the moment. So the ones that are just a little bit to the left of the top edge there, those fountains of gas streaming up are taller than the Earth by quite a ways. So they're amazingly large. I do want to point out that this view that the video camera captures is pretty awful compared to what it would look like looking visually through Jim's telescope now. It's the same effect if you saw our moon streaming session that we did just recently. the images that we could show you through a video camera through the telescope for about 100th as good as they actually would have looked to your eye looking through that same telescope at the same time. So because the camera struggles to handle the difference between the brightness of the bright face of the sun and the relative faintness of these streamers of gas coming off the sun. Jim can change the exposure, the histogram of the view, and dim it down quite a bit. We'll lose a lot of those faint prominences, but the sky will get darker and we'll see more of the surface. You can see that the surface of the sun is not perfectly uniform. It's very mottled looking. It looks kind of like the surface of an orange or something else very pebbled like that. That's a real effect. Again, the view is the video camera doesn't do it justice of what the telescope is really providing, but that's a real view you're getting there of this mottling on the surface. Now, if there were a lot of active areas, there were a little bug or a bird flying past. Sometimes you will see things float past in the view of the sun in the live view. The mottling is always there. That's the boiling of cells of gas along that photosphere surface of the sun that we're looking at, that 10,000 degree surface, and up into the chromosphere that we're looking at here in the hydrogen gas too. And they're always there, but if there were other big prominences, when you look down on those, they look like a shadow in hydrogen alpha. So they look like dark squiggles going across the face of the sun. If there are sunspot groups, you often see bright squiggles around them where there are basically sort of cracks in the atmosphere where more heat is streaming outwards and we're seeing hotter gas. So there's a lot of surface detail that you see in a view like this, potentially, again, if the sun is more active. I'm going to switch back to sharing here, if I can. There we go. So many different screens. We'll do that one. Again, this was a live, relatively very recent image in white light of the sun. If we look at this image, we can see this is actually the group of prominences here up in the upper right that we're looking at with Jim's telescope. If I go over here and drag this picture over, this picture was taken about 45, almost an hour ago now. This is that group through a hydrogen alpha telescope in Colorado. There's a set of observatories all around the world that are continually that are earthbound observatories that are continually watching the sun too. And so online through this Gong is the name of the program, researchers can almost get a live view of the sun all the time in hydrogen alpha. You can see the H alpha. Again, this is this red line wavelength that we're looking at here. So that's that group. This is more like the view that Jim would see visually looking through his telescope, much sharper like this without the overexposure of the bright areas, because your eye can adapt much better than the video camera can. So there's that. I wanted to show you the surface of the sun in white light. This is an amazing picture taken by a new telescope, which is just in Hawaii, the Inouye Solar Telescope, which is just being commissioned now, that will give the closest and most detailed views of the surface of the photosphere of the sun that we've ever had. So these are those cells, those convection cells. This gives the effect called granulation on the sun that I was mentioning, this view is close enough that this little group, this little cell right here is about the size of the state of Texas. So this is how much we're zooming in to the surface of the sun. If we go back to a white light image, I shouldn't close that one. Let's see. Yeah. So, yeah, let's just go to this. We go to a white light image, and this is how the sun would look through Jim's other telescope in white light. The one thing we do see, even though there's not much going on except for this one little sunspot group and a couple of light patches around it, is that when we look at the sun, the center of it looks brighter than the edges do. It gets fainter as you go toward the edges. This effect is called limb darkening, L-I-M-B, limb as in a tree limb or arm or leg or whatever. So it's limb darkening, and it's a real thing that you see. There was a lot of conjecture for what causes it, because people could see this looking at the sun through specially equipped telescopes for a long time. We now know that the cause of this getting fainter towards the end, it isn't something to do with telescopes. It has to do with the surface of the sun. With these granules, these are very three-dimensional. They're bumps, and the tops of them tend to be hotter and therefore brighter. And then the sides of these hills, of these bumps, are cooler and darker. This is where hot material is welling up, and then it cools off by radiating out, and then it sinks back down around the edges, kind of like bubbling, very much like bubbling liquid. When you're looking straight down at the middle of the sun, you're seeing a lot of these tops shining at you. When you look over toward the edge of the disk of the sun, you're actually looking at the sides of all of these little bumps, and they're fainter, and so this is what causes limb darkening. Let's go back to Jim's image. I'm going to stop sharing, and I will spotlight Jim. I can't spotlight Jim. So Jim, can you share us back with your H-alpha view? There we go. I would say, doing solar observing like this, I also have a telescope. I have a pair of telescopes like Jim does, and one of them I can watch in this hydrogen alpha view, and the other one I can watch in the white light view. One of the most interesting things about the hydrogen alpha view is these features change while you're watching them. You can see the material moving in these over minutes in time. You'll see a little thing like this bump here, and look at it in 10 minutes, and it'll either have extended up, or it might have shrunk down and disappeared or something or other. It might break away. So you're actually watching activity on the sun, which is amazing. Both of these kinds of telescopes, of course, are made to be extremely safe for us to use. You can't point a regular telescope that you would be looking at the moon with, or the planets or other stars or things with, at the sun and look through it, because the intensity of the light coming out of it would be enough to burst paper into flame and certainly blind you. So you need to have special equipment. The white light viewing, the normal light viewing, can be done with a fairly inexpensive but properly made filter to block the light before it comes into your telescope. And this kind of filter, we just call them a solar filter, they will block out all but 1/1000th of a percent, or in other words, about 100,000th of the light coming in before it even gets into the telescope. It only lets that tiny fraction into the telescope, when the telescope then does its regular job of providing you a magnified view of things. So that's a safe way to view. The hydrogen alpha viewing is a little more limited. There's only one thing you can look at with this setup, and that's our sun, because it's the only star near to us. And it lets through so little light that there's no other objects bright enough that you can view with them. So Jim has a setup where his filtering is done primarily at the eyepiece end, and he can put that on a different telescope. My hydrogen alpha telescope is a dedicated telescope that I can't look at anything else with. So it's kind of a specialty part of our hobby. But when we have public activities again, we normally once a month, spring through fall, have what we call our Solar Saturdays, and we gather on the Naperville Riverwalk and park there and set up telescopes like this for you to look through. So we are not doing those currently, obviously, because we're still being careful about our gatherings. But when we get back to doing those again, we would like you to join us at our Solar Saturdays. Jim, is there anything else you wanted to share to talk about, or?
Not really. I can tell what my setup is here if anybody cares. Sure. So the mount is a Celestron Advanced VX mount. It's an equatorial mount, and this is an Explore Scientific 80 millimeter refractor. And this part back here, I don't know if you can see that where I'm pointing, but this kind of red and black part, this is the hydrogen alpha eyepiece that's going into this. So this is a normal nighttime telescope that has this special part here that's doing all the hydrogen alpha. And then I have a camera on the end right here. So, yep.
All right. Thank you. I'm going to go back to sharing. I just wanted to talk briefly a moment more about some things on the sun. So the sun is a big magnet, and it has magnetic field lines, just like you would see if you on any kind of magnet. Here's the classic thing of putting iron filings around a little bar magnet where you can see the field lines that go from pole to pole. So the sun has very complex magnetic field going on it. It's a fairly strong field, but the sun isn't a solid body. It isn't a bar magnet. It isn't solid like the Earth is even. It's a ball of gas. And so instead of being very stable, it actually is always churning. The equator of the sun actually rotates faster than the poles do. So the sun is always kind of twisting itself up, and its magnetic field gets twisted up. So all of this activity of this really hot gas that we're seeing, these prominences and this gas streaming off the sun, is all charged. It's all ions, so plasma. And so it is constricted by the magnetic fields of the sun. So I wanted to share you a video of, I'm going to drag it over here, of, this is from the SDO, the Orbiting Solar Observatory of NASA. And so you can see an active area on the sun here. The light, again, looks funny. We're looking in, this is actually not hydrogen alpha light, but a different, close to it, frequency of very hot radiation in the ultraviolet. And so I'm going to start this video from where it's going. This is an active area on the edge of the sun. So the sun looks dim here again in this hydrogen view, in the ultraviolet hydrogen view. And this very active area is bright because it's radiating more energy, and there's gas streaming out. But I'm not going to show this entire video, but it's really interesting to see this time exposure, this time loop sped up of what this gas is doing. We've got a large prominence that's overloading the sensors on the satellite here. It's so bright, forming. But the gas doesn't just stream up it follows the magnetic lines and it streams back down. You've got gas from the sides. All of these lines, these jets are following these magnetic lines, these loops of the sun. So this is what we're seeing. Here is how big what we're seeing is in a prominence like this. Again, this is probably about the height of the prominence you were just looking at on the edge of the sun through Jim's telescope in live. Jim's not seeing quite this view. This is actually over some hours of time that this sped up loop was made. But the physics here and what we're seeing here is just amazing. It's just incredible. And again, we can't quite see this detail through our amateur telescopes, but you can see this general effect of this growth and things changing over time, which is really quite amazing. There's not much in astronomy that goes fast. A lot of astronomy just sort of sits there. But on the sun, we can watch changes happen sort of minute by minute. I don't see any questions or comments in the Facebook section. We are going to retire soon. This was going to be a short session. So if anybody has anything that they would like to ask us, the Facebook comments is the place to do it at the moment. I did want to say that we're going to probably do more solar sessions. This was our first stab at it. We'll just have to see what the sun does for us as far as providing sunspots or anything to look at. We may have to wait a couple of years before we have a lot of sunspots again, but you never know, because it's kind of, from our Earth point of view, it's sort of a random thing. There's really no way of predicting when they're going to pop up. It's just that we should be through the solar minimum, and we should start to be seeing more sunspots before long, but that's a hard bet to figure on. Otherwise, I would recommend if you just go to your favorite search engine and look for current solar images, space solar images. There's tremendous resources out there. Things like this video from NASA are all free and public domain, and they're waiting for you to watch. There's endless things. There are several professional solar observatories going that all have websites that will have fairly current information too. So there's a lot available there. Otherwise, I don't see any other questions. So I think we're ready to stop the stream and say so long for today. We do, I should announce, we do have this Tuesday. I have to look over here at my calendar. We have our streaming of our Astronomy Fundamentals program for our club. Fundamentals is our second indoor program of the month, and it's always on a topic for more the beginner level of things. In this month's program and next month, the June and July programs, we are going to have a family focus and have kid-friendly activities and short little presentations about stuff. So it's family week. So that'll be Tuesday night at 7:30. This is on the 16th. And you will find us streaming here on Facebook, and you will find us embedded on our naperastro.org website streaming page also. So with that, I'd like to say happy Sunday to everyone, and get out and enjoy the blue sky if you're in a part of the country here, like it is where we have some blue sky and nice cool air.